Right, in this lesson, we're going to be taking a look at some useful applications for logarithms and exponential functions. One example, one real life use for logarithms and exponential functions is compounding interest, exponential growth and decay, as well as half-life. Half-life is used quite a bit in the sciences and chemistry and biology. So the formula for continuously compounding interest is A equals P e to the RT power, where A is the amount, P is the principal, R is the rate of interest, and T is the time in years. So if we have an example where it says you invest in an account that compounds interest continuously at 5%, how long will it take to go from $300 to $3,000? So we use that formula for continuously compounding interest. The principal amount is 300. The amount that we end off with is 3,000. E is a constant. Our rate is 5%. We never use the 5% in calculations. We always use the decimal equivalent, which is 0.05. We're trying to calculate T. How many years will it take using compounding interest continuously to go from $300 to $3,000? The first thing we do is divide both sides by 300. And then we have an exponential function that we want to write as a logarithm. Or actually what we don't want to write it as a logarithm. It would be easier to just take the natural log of both sides. So on the left side we've got natural log of 10. On the right side we've got natural log of e to the 0.05 t power. Now on the right side, since we have log base e of e to the 0.05 t, that is the same thing as 0.05 t times the natural log of e, and then we can divide both sides by natural log of e is just 1. That's log base e of e to the 1 power, which is just 1. And then to solve for t, we would divide both sides by 0.05. And we get approximately 46.05 years. For exponential growth and decay, we use the following formula, where the plus is used for exponential growth, the minus for exponential decay. A is the initial value, R is the growth or the decay rate, X is the number of time intervals. So in example 2, it says the population grows from 1,200 to 3,600 in 5 years. How long will it take for a population to double? How long will it take to quadruple? So we use the same formula, that exponential growth formula. We start off with 1,200, so A is 1,200, and we end up at 3,600, so Y is 3,600. X is 5, because it takes 5 years to go from 1,200 to 3,600, and we're trying to calculate the rate. So we divide both sides by 1,200. We get 3 equals 1 plus r to the 5th power. Alright, and then we want to do the opposite of raising to the 5th power, which would be raising to the 1/5 power, both sides. Get 3 to the 1/5 equals 1 plus r. And then we get r equals 3 to the 1/5 minus 1, which is approximately 0.2457. So now we know the rate of growth. So to determine how long it would take to double, 1,200 doubled is 2,400, so we just use that rate plus 1 plus 0.2457 is 1.2457. So we divide both sides by 1,200, and we get 2 equals that amount, take the natural log or common log of both sides. Bring the x down to the front of the logarithm, and then divide both sides by the natural log of 1.2457. And when we approximate that value, the natural log of 2 over divided by the natural log of 1.2457 is approximately 3.15 years. To see how long it would be to quadruple, on the left side of the equation we would just have 4,800. And when we divide 4,800 by 1,200, the initial amount, we could just get 4. And we follow the same steps. Take the natural log of both sides, bring the x down in front of the logarithm, and then divide both sides by the natural log of 1.2457, and we get approximately 6.31 years to quadruple. And the last type of problem is going to be a half-life problem. This is the formula that you would use for half-life, where n sub 0 is the initial quantity, n sub t is the remaining quantity after time t, and then t sub 1/2 is the half-life. So in this example it says you have 100 grams of a substance that goes to 10 grams after 66 days. What is its half-life? So we start with our n sub 0 is 100. It goes down to 10. So n of t would be 10. And then t is the 66 days. So we divide both sides by 100. 10 divided by 100 is just 1/10. And then we take the log or natural log of both sides. It really doesn't matter. I take the common log of both sides. I get t to the 1/2 equals 66 over log base 1/2 of 1/10. What I did was I just interchanged the log base 1/2 of 1/10 and the t sub 1/2, because that's what I'm trying to calculate, that t, that half-life. So whenever I divide 66 by log base 1/2 of 1/10, I get what I did was I used the to calculate log base 1/2 of 1/10, I just used the change of base formula. So if you don't have a calculator that allows you to change the base or evaluate a change of base, you can rewrite log base 1/2 of 1/10 as the natural log of 1/10 divided by the natural log of 1/2, which is the same thing as 66 times natural log of 1/2 divided by natural log of 1/10, which is approximately 19.9 days.